Deactivated state. This is the most important of switch characteristics and governs how switches function when deployed in a circuit. Notice the careful use of terminology I've employed throughout this lecture. At no time have I said on or off, but rather limited myself to saying closed or open. Let's clarify my careful use of terminology up front and establish some limits and expectations. Making means the act of closing an electrical connection. Breaking means the act of opening an electrical connection. I ordinarily use the term actuation to mean the act of hitting, punching, poking, flicking, twisting, or otherwise diddling or dorking with a switch. An actuated switch can do one of two things. It can make or break a contact, i.e., a switch can close or open. This implies an important fact. The switch, prior to being hit, punched, poked, flicked, twisted, diddled, or dorked with, had a natural deactivated state to begin with. All schematics, all the time, are always drawn in their depowered state, a point I will come back again and again to tediously belabor. We'll soon discuss switches held in their activated state when the system is depowered. However, for now you must simply understand and differentiate between the two mutually exclusive states of deactivated and activated. People use all sorts of weird terms for these two states. However, in an effort to establish some clarity and consistency, I will always refer to them as deactivated and activated. Switches, by being actuated, can transition from their deactivated state to their activated state and vice versa. An electrical load, in contrast, is de-energized or energized. An electrical load would be a lamp, a coil, a buzzer, or a solenoid, or anything that draws current and is put to some recognizable use. A de-energized electrical load experiences no current flow through it. An energized electrical load does experience current flow through it. Please do not use the terms unperturbed or perturbed, as is common in some countries when describing switches and electrical loads, nor apply the terms commonly reserved for switches to loads, nor those terms commonly reserved for loads to switches. It perturbs me to no end. Stick with the terms I'm using, and we'll get along just fine. Again, I'm looking to establish clarity and consistency. Switches are identified using their natural deactivated state. This brings with it an important distinction. A switch, when in its natural deactivated state, can be in one of two normal positions, closed or open. A normally closed switch, in its deactivated state, as the name implies, is closed. This is its natural deactivated state. When actuated, it transitions to its activated state, that being the opposite of deactivated. A normally closed switch, when actuated, opens. It makes sense. A normally closed switch is normally closed when you're not poking it. When you poke it, it opens. In contrast, consider a normally open switch. A normally open switch in its deactivated state, as the name implies, is open. This is its natural deactivated state. When actuated, it transitions to its activated state, that being the opposite of deactivated. A normally open switch, when actuated, closes. It makes sense. A normally open switch is normally open when you're not poking it. When you poke it, it closes. Let's put this understanding to a test. What is the resistance of a normally open switch, often abbreviated NO switch, when it is deactivated? In its deactivated state, it should ideally present infinite resistance because it's open. In its deactivated state, a normally open switch will not allow current flow through it and should have a voltage drop across it depending upon its position in the circuit. What is the resistance of a normally open switch when it is activated? In its activated state, a normally open switch, it should ideally present 0 ohms of resistance because it's been closed. In its activated state, a normally open switch will allow current flow through it and should not have a voltage drop across it. Consider the entirely opposite scenario. what is the resistance of a normally closed, often abbreviated NC, switch when it is deactivated? In its deactivated state, a normally closed switch should ideally present 0 ohms of resistance because it's closed. In its deactivated state, a normally closed switch will allow current flow through it and should have no voltage drop across it. Finally, what is the resistance of a normally closed switch when it is activated? In its activated state, a normally closed switch opens and should ideally present infinite resistance because it's been opened. In its activated state, a normally closed switch will not allow current flow through it, and it should have a voltage drop across it, depending upon its position within the circuit. Notice I'm using a slightly different schematic than the single-pole, single-throw toggle switch we've previously employed. The single-pole, single-throw toggle switch was something known as a single-break switch, in that there is a single point where the single pole breaks or makes its contact with its single throw. This normally open and normally closed switch on the left-hand side are still kind of like SPST switches, because each switch has one moving contact, and it can only be placed in one position. However, they're both known as double break switches, because there is now 2 points where the single pole breaks or makes its contact with its single throw. A switch with double breaks provides a greater volume of contact material, permitting greater heat dissipation, longer switch life, and greater breaking capacity. Now consider 2 of these types of switches housed in a single package, one being a normally closed switch from terminals 1 to 2, and the other being a normally open switch from terminals 3 to 4. Switches are often paired together in packages with a mechanical interlock between the 2 switches. The mechanical interlock is the dashed line. Terminals 1 and 2 are electrically isolated from terminals 3 and 4. However, when an operator actuates a single button on the outside of the package, the normally closed side opens and the normally open side closes. Think of this as 2 electrically isolated, mechanically interlocked switches, both with double break contacts. This is often called a break-make push-button package because when you actuate the single push button, the top switch opens and the bottom switch closes. Such a switch package might be employed to our advantage by preventing one electrical load from being energized when another is being turned on. For example, you would never try to simultaneously spin a 3-phase AC motor, clockwise and counterclockwise at the same time. Not only will it destroy the contactor by going phase to phase in an arc flash hotter than the sun, it flat out doesn't make sense. And a mechanically interlocked package of a normally closed and normally open switch can be employed to prevent some dummy from trying to do so. Finally, let's review activation period and differentiate between momentary and maintained contact. A momentary contact switch only remains activated when it is being actuated. If a momentary switch isn't being actuated, they remain in their deactivated state. An example of a momentary switch might be a spring-loaded push button that enters its activated state the moment you press it, and instantly returns to its deactivated state the moment you stop pressing it. The keys on your keyboard are momentary switches. In contrast, a maintained contact switch stays in one state until reset or actuated into a new position, and then it remains in that state until actuated or reset once again. This is like a light switch in a house. When the lights are off, you hit the switch and the lights come on. When you take your finger off the switch, the lights stay on because the switch maintains the closed state until you hit the switch again, which returns it to its open state. Think of how hard it would be to get anything done in your house at night if you had to keep your finger on the switch the whole time to keep the lights on. Let's take a look at some switches commonly employed in electrically controlled systems and see if we can apply the terms normally open, normally closed, and momentary versus maintained to their construction and electrical characteristics. The first example of a manual switch is an emergency stop button, sometimes called an EMO for emergency off, ESTOP, or oh shit button. Emergency stop buttons are ordinarily characterized by a conspicuous red mushroom-shaped actuator placed in an easily accessible location. This example ESTOP has 4 terminals, one pair of terminals being a normally closed switch from 1 to 2, and the other pair of terminals being a normally open switch from terminals 3 to 4. The schematic indicates there is a mechanical interlock between the 2 switches. When the mushroom head actuator is pushed, the top switch from 1 to 2 opens, and the bottom switch from 3 to 4 closes simultaneously. ESTOPs, for obvious reasons, are ordinarily maintained switches. It makes sense. That's what you typically want an emergency switch to do. If you press it once because you're in a dangerous situation, you'd like that dangerous situation to not only stop after you hit the button, but also stay stopped. Only when the ESTOP is reset will it return to its deactivated state. Sometimes you'll see the maintain contact and reset on the schematic, sometimes you won't. Quick note on resetting emergency stop buttons. Resetting an ESTOP isn't as simple as pulling the mushroom button back out. Normally they need to be rotated a half turn for it to be reset. Sometimes the face of the button has an arrow to remind you of this necessity, sometimes it doesn't. Additionally, sometimes emergency stop buttons have a green ring on the stalk of the mushroom to indicate that the switch is in its deactivated, ready, or go state. Look at emergency stops from the side and make sure you see the green band before you return the equipment to service. Because they're placed in easily accessible locations for quick access in an emergency, the same location means they're easy to accidentally bump. Sometimes emergency stops in high traffic areas employ guards that allow the button to be actuated in an emergency, but prevent it from being bumped by a cart or your backside.